Let's talk a little bit about how to use the properties of Laplace's equation to find solutions to Laplace's equation in certain regions. So if you remember, two properties of Laplace's equation that turn out to be very useful are that, one, the maximum and minimum values of the electric potential, which solves Laplace's equation, only happen at the boundaries and cannot happen in the inside of the region. The other useful property is the first uniqueness theorem, which says once you've found a solution that satisfies the boundary conditions, you found the only solution. So if you can guess it, if you can guess that solution, then you've found the right one. So let's see how this works in practice in a couple simple examples. So here is an example. We have a box with conducting walls, and all of the walls are set at an electric potential of 0. And inside the box, it's empty. So we have empty space. So Laplace's equation is the equation that determines what's happening inside that box. And v, in principle, could be a function of x and y coordinates. And so what we want to know is, what is the electric potential inside the box? Well, we do know that v must be 0 on the boundaries, because the walls are all at 0 electric potential. And inside the box, the electric potential must satisfy Laplace's equation, which turns into the sum of the partial derivatives in the x and the y direction. The second derivatives must be 0. Okay, well, let's see again if we could guess a solution. And if we can guess a solution, then that satisfies the boundary conditions, then it's the solution. So I'm going to guess a solution based on this first property, that the maximum and minimum values can only happen in the boundaries. And since the max and min can only be on the boundary, well, and the boundary everywhere is v is equal to 0, that means that v must be 0 everywhere inside. You can see that this must be true, because if v was something that was non-zero inside of the box, then that would be either a minimum or a maximum, and that can't be possible. The maximum and minimum can only be on the boundary. That seems a little slick, doesn't it? Well, we can just check. Again, it satisfies the boundary conditions, and it also satisfies the requirement that the Laplacian is 0. So Laplacian of 0 is 0 everywhere inside. And so, indeed, it satisfies those two. By the uniqueness theorem, a solution is the solution. So this is the solution inside the box. It certainly seems a little bit quick and a little bit too slick, but it turns out that is indeed what the solution is inside the box. The electric potential is 0 everywhere inside. Now you might be wondering, is there ever a case where I get a non-trivial solution where I actually have to do any work? And indeed, there is such a solution, or such a case, where, for instance, you have an electric potential of 0 on the left and right walls, but a constant electric potential of, say, V0 on the top and the bottom of the box. In this case, the electric potential must satisfy these boundary conditions, but the boundary conditions are a little bit more complicated. And it must satisfy Laplace's equation in the interior of this box. And it turns out this requires a bit more work to come up with a solution in this case. We can't just guess the solution like we did in the previous case. So we're going to have to use a technique called separation of variables to find the electric potential on the interior region here. More about that later, but for right now, just keeping in mind that it doesn't always work out as easy as that previous case where we had an electric potential that was constant everywhere inside. Let's look at another case. Let's look at a case with spherical symmetry. And so we have a spherical cavity with a wall that is all at a constant electric potential of V is equal to V0 over the spherical shell, which is the wall of this boundary of the cavity. And we want to know, what is the electric potential inside the cavity? Well, the electric potential must be V0 on the boundary, and it must satisfy Laplace's equation. But Laplace's equation in spherical coordinates looks pretty ugly, and so we might be really intimidated about guessing a solution to this because it's not a nice-looking Laplacian for spherical coordinates. But it turns out we can still guess, again using this first property of Laplace's equation, that the max and min values of V can only be at the boundaries. And since the boundary is all at an electric potential of V0, the electric potential has to be V0 everywhere inside. It has to be V0 everywhere inside, because if it was something different, then that would be either a maximum or a minimum that's not at the boundary. Again, it seems a little slick, but it satisfies the boundary conditions. It satisfies Laplace's equation. The Laplacian of a constant is indeed 0, even in spherical coordinates with those weird derivatives that we have to take. And so by the uniqueness theorem, it is the solution. Let's look at one more example where we get something maybe that's a little bit non-trivial. We looked at the inside of the spherical cavity. Let's look at the electric potential outside of the spherical cavity. In this case, it's still empty space outside the spherical cavity, outside the shell. And so the electric potential obeys the Laplacian of the electric potential is equal to 0. And so we can ask, what are the boundary conditions then? Well, certainly the electric potential is V naught, a constant, at the radius of the spherical shell. And then there's one more boundary I put in quotation marks here because the boundary of the space outside of the spherical cavity is actually at infinity. Imagine a spherical shell with infinite radius. That's the other boundary that we have. And so we want the electric potential to be 0 on that boundary because otherwise then the electric potential would blow up at infinity. That doesn't seem like a good idea. And so we'll demand that the electric potential goes to 0 as r goes to infinity. And we must have something that satisfies Laplace's equation in spherical coordinates. Well, now it's a little bit trickier to guess this solution. We can't just guess a constant, and in fact the electric potential is not a constant in this region. But we can guess something that's still pretty simple. So I'm just going to guess something that is V naught, big R over little r in the outside region. And this guess is motivated by the fact that, well, if I put little r is equal to big R, then I get V is equal to V naught at the surface. And if I take r goes to infinity, I get 0. And so this satisfies my boundary conditions. You might be wondering whether it satisfies the Laplacian is equal to 0 in spherical coordinates. And indeed it does. You can check it. In particular, it is really important that it was 1 over little r, the spherical coordinate r, in this case, instead of 1 over r squared. So 1 over r was absolutely essential for this to satisfy the Laplacian is equal to 0. But you can check that, and indeed it satisfies that the Laplacian of this is 0. And so since it satisfies the boundary conditions, and since it satisfies the Laplacian is equal to 0, it is the solution to this problem. So that's pretty cool. That tells us that we have found the electric potential both inside and outside of the spherical cavity essentially just by guessing. We never actually really did a calculation, unless you count calculating the Laplacian outside the sphere, just to make sure that that indeed was 0. But we just guessed our solutions, and because of uniqueness, the first uniqueness theorem, we knew that it was the solution. So we didn't have to do a calculation. So we know the electric potential as a function of r looks something like this. So again, that's the power of Laplace's equation and the uniqueness properties of solutions to Laplace's equation.